Hello everyone, I'm Gilead Levy. I'm going to present to you an extended summary of a work of mine on graphical partitions. Actually, it's a summary of a paper that I wrote and it is available on arXiv now on graphical partitions. So let's begin. An integer partition of a natural number n is a finite sequence of integers that sum up to the same number n. A graphical partition is an integer partition such that each of its parts corresponds to a degree of a node in a simple graph. Here is an example of a simple graph that corresponds to the integer partition 1, 1, 2, 3, 3, a partition of 10. Indeed, we see that each part is a degree of one of the nodes in the graph. So this integer partition is actually a graphical partition. The mathematician Pittel established that the probability of a random integer partition to be graphical tends to zero as n increases. In 2016, he also found an upper bound for the decay rate of this probability. And you can see that his estimate decreases very slowly as n increases. The main result of our work is to establish another upper bound for this probability that depends only on the Delphi square side length of the partition that we consider, instead of it being dependent on n. Another new insight of our paper is to prove that this new upper bound actually holds even if we restrict the parts of the partitions to come from prescribed sets, such as even numbers, odd numbers, perfect squares, perfect cubes. In all of those cases, our upper bound still holds. So in our derivations, we represent the restrictions placed on the parts using a continuous function denoted here by mu, such that mu of I is the ith smallest allowable part that the partitions can have under the restrictions imposed on them. Using a continuous function to represent the restrictions allows us to use methods from calculus and differentiate this function such that that will be convenient in our derivations. In our work, we only consider functions mu that are continuous, differentiable, and strictly increasing. Of course, that those conditions don't limit the restrictions that can be placed on the parts. Okay, so for most of the restrictions that can be placed on the parts, that is for most functions mu, the number of integer partitions of a number n have actually been enumerated. Here is an example of the asymptotic expression for the number of integer partitions of n that have only perfect square parts. Here zeta denotes the Riemann zeta function, which is also a nice example of how unique and exotic the expressions in this topic can actually be. But anyway, the number of graphical partitions of n that have only perfect square parts have not been enumerated. This is one of the problems that our paper aims to solve. So, as I've explained in the beginning, the main result of our work is to establish an upper bound that depends only on the Delphi square of the partition. So let's recall the definition of the Delphi square. It is essentially the largest square that can fit in the first diagram of the partition. So here we have an example, the first diagram of the partition 6, 5, 3, 3, 1, 1, 1. Each row of the diagram corresponds to one part in the partition. For example, the first row corresponds to 6, the second to 5, the third to 3, etc. And the bold area is the Delphi square of the partition. So you can see that in this case, the side length of the Delphi square of the partition is equal to 3. In our derivations, it is also convenient to use the definition of the successive ranks of the partitions. In order to formally define the successive ranks, we shall denote by x sub k the number of parts of the partition that are larger than or equal to k, and also denote by y sub k the kth largest part in the partition. Then the kth successive rank of the partition is defined by the difference between those two quantities, that is y sub k minus x sub k. It is convenient to us to use the definition of successive ranks because of a condition formulated by Nash-Williams for an integer partition to be graphical. It essentially means that an integer partition is graphical if and only if the partial sum of its first d successive ranks is less than or equal to minus d for any natural number d that is smaller than the Durfee square of the partition. Now that we went through the condition of graphicality that we use in our work, we shall dive into the probabilistic model that we use. We actually use the model that was formulated by the French mathematician Fridet. According to his model, the multiplicity of a part equal to k in a random integer partition follows a geometric distribution with a parameter q. Then, if we condition that the integer partition has a sum of n, then this condition translates to an equation. We can write n in terms of a sum of the parts k times their expected multiplicity in the partition. Then, since the parts come from the image of a function mu that represents the restrictions on the parts, then we can replace k by mu of I and set I to run from 1 to infinity. Afterwards, we evaluate the expected value using the geometric distribution, and thus we have an explicit expression that depends on the parameter q. We can bring this equation to a slightly simpler form by setting alpha to be equal to minus log of q. Then you can see that the right-hand side depends only on the function mu and the parameter alpha, while the left-hand side is simply n. So we essentially found an equation for the parameter alpha in terms of n and the function mu. And thus we evaluated the parameter of the probabilistic model in terms of the number n and the restrictions on the parts. So some specific cases, if the parts are not restricted at all, that means that each part can have any natural value, then we can set mu of I to be equal to I for any natural number I. Then using asymptotic analysis, we can evaluate alpha and find that it tends to 0 as n increases. But rather, if we set the parts of the partitions to be perfect squares, then we find that alpha decreases with n in a slightly faster pace. In general, for any restriction placed on the parts, the parameter alpha of the probabilistic model tends to 0 as n increases. A major stepping stone in our derivations is to show that the asymptotic distributions of y sub k and mu of x sub k are the same as n increases. We once again recall that y sub k is the kth largest part in the random integer partition, and x sub k is defined to be the number of parts in the partition that are equal to or greater than k. So in order to formally explain this, we must define another function eta that depends on the number n and the function mu. Notice here that the dependence on the number n comes from the dependence of the parameter alpha on n, as we have seen in the previous frame. So we see that the cumulative density functions of eta of y sub k and eta of mu of x sub k approach the same function represented here by an integral as n increases. So we can deduce that the asymptotic distribution of y sub k and mu of x sub k are also the same. Um, Afterwards, by evaluating the distributions of y sub k and x sub k, we can directly determine the distribution of the successive ranks by the definition of the difference between those two quantities, that is y sub k minus x sub k. And then finally, in order to apply the condition of graphicality formulated by Nash-Williams, we must find the distribution of the partial sums of the successive ranks. We denote the cumulative density functions of these partial sums by the function capital F. Notice that since the successive ranks are independent of each other, as we sum on more successive ranks, that is, as d increases, we expect the cumulative density function to approach a normal distribution, a standard normal distribution from the central limit theorem. So using Edgeworth expansions, we actually can determine the rate of convergence of the cumulative density function into a standard normal distribution. And we see that as d increases, we sum on more successive ranks, and the two distributions become more similar. Then, after using some more several lemmas that we elaborate on more in the actual paper, we prove our main theorem and find that the probability of a random integer partition to be graphical is bounded from above by this expression that depends only on the Delphi square side length of the partition for any restriction placed on the parts. But note that this theorem holds only if only for sufficiently large Delphi square side lengths, and we demand that d and n are independent of each other. Okay, so as a result of our main theorem, we can actually formulate another upper bound in terms only of n and the function mu. Here we denote the probability of a random integer partition of n with the restrictions represented by mu to be graphical by the function p and mu. Then we notice that since all the parts come from the image of the function mu, the Delphi square side length is bounded from above by the inverse function of mu evaluated at the square root of n. And so plugging this in the main theorem, we find the limit inferior identity. This essentially means that we found an upper bound for the probability using explicitly the number n and the function mu instead of the Delphi square. This is also obvious proof of a generalization of Wolff's conjecture. Originally, the Wolff's conjecture said that the limit inferior of p of n of this probability will be 0. But now we proved it also for any restriction mu placed on the parts. And we actually found an estimate for the rate of the decay. So here is a nice example. If we once again restrict our parts to be perfect squares, then we have the following limit inferior identity, which is quite non-trivial. So to summarize, our work considers graphical partitions, and shows that their distribution not only depends on their sum n, but also on their Durfee squares classes. So that's it, and thank you very much for your attention.